Archimedes Law of Gravity. Take one. Always wanted to do that.
All right.
Let's roll.
Okay, so we're going to go into Archimedes Law of Gravity. This is a new law of gravity. It came about when I was very, very bored. I decided to do an experiment that I had been wondering about for about 2 years. And then I got really, really bored, and I did the number experiment, and my eyes got really big, and I went, no way, that can't be. And this is the outcome of that. So Archimedes once was hired to find out if a gold crown was pure gold or if it had been mixed in with some silver. So he had to measure the density of the crown of the king of Syracuse, I believe. And so what he discovered is he got into a bathtub, the bathtub overflowed, and he said, "Eureka, I have it." And he ran through the town naked, yelling, "Eureka, Eureka," because he had figured out that the way to measure volume was that you could dunk a body into water and watch how much water was displaced, and that would give you the volume of an irregularly shaped object. He could now find the volume of the crown, and then he could weigh the crown and get the density of the crown. And he also found the buoyant force in the same way. When you float an object on water, the weight of the water displaced by that volume is the upward buoyant force on the thing. And we're going to find that in Archimedes' Law of Gravity. And that's why it's named after him, is this thing is eventually going to show up again. Okay, so here's the experiment. And we're going to start off with some data. And means of destruction, I'm going to ask you to please look up the value of the universal gravitational constant. And we're going to use it in two number systems. We're going to use, or measurement systems, meters, kilograms, and seconds, and also in centimeters, grams, and seconds. So this is universal gravitational constant, G. This comes from force of gravity equals G M1, M2 over R squared is Newton's famous law of gravity. And what I'm going to do with this number is I'm going to notice that when Newton wrote his equation, he arbitrarily put G in the numerator. He could have put it in the denominator, and it would have been completely the same. The number would have been different. It would have been the reciprocal. So this thing could also be written as M1, M2 over G to the negative 1 power R squared. Because G to the negative 1 power is the same as saying 1 over G. That's what negative 1 power means for all those people who need a little review. So I thought maybe I might like to look at the universal gravitational constant upside down. So that was the whole thing that I was like, spent 2 years thinking, I should really look at that upside down, see what that is. And one day I did. So if you could please give me Newton's gravitational constant.
All right, so Newton's gravitational constant in SI is 6.674 times 10 to the negative 11.
Give me the rest of the digits here.
730, and that's what we have.
Uncertainty?
Uncertainty of 15.
15.
Yep.
Times 10 to
The negative 11.
negative 11th.
Meters cubed.
Meters cubed.
Kilograms to the negative 1.
Kilograms down here.
Yep, and then second squared in the denominator.
And second squared in the denominator. All right. Now, if I change the units of this thing to centimeters, grams, and seconds, this power of 10 is going to change. Do you have that?
Yep. We get the same number, except it's 10 to the negative 8. We express that in dyne centimeters cubed over grams squared.
Or it has the same format. So I see length here, grams down here, and second squared down here. Okay. Now, what's G inverse? So if we have G negative 1, let's do this in like 10 to the negative 11th. On a calculator, if we take G 6.6743015, that actually means that it's in the range of 15 here, or 6.67415 up to 6.67445. That's the range. Okay, that's what those numbers mean. So what's the inverse of 6.67430?
It's a very familiar friend. It's 1.498.
Okay, any more digits?
Let me grab. I gotta put it manually if I.
Oh wait, we don't know that yet.
7.4. That's just.
We don't know that yet. So the middle number, 6.67430, uncertainty 15, we got 1.498. We should get the range here.
Yeah. Okay. All right. So it is 1.4982844. How many digits do you want?
You know, that's okay. I think what I'm interested in is I want to define this bracket down here. So did you just do the 30?
Yes.
Okay, great. We'll just go with that.
Okay.
So let's do the 15. 6.67415.
Change the 30. All right. So that will give us 1.4983181.
Okay, and the 6.67445.
45 is 1.498250079.
I'll just take that 8 at the end. Okay, so we see that 1.498 is the same. It begins to get a little different here. So if we take the 28, let's see, so that would be off by 4. That's off by, okay. So I think I can say the range like this. Is that correct? Or just actually it's just a 4? So are these two numbers inside that range? Okay? All right. And so we're going to work with 1.4982884.
Why not 3?
You want to do 3? Well, 28 plus 3 would give us the 31, but wouldn't take in the 81.
Yeah, I'm ignoring the 81 because we only had 6 digits about the information.
Well, but this would turn into a 32.
Okay.
Right? 32 and 2508. So we're pretty comfortable with those. Okay. So what about the power of 10 times 10 to the something? And we flip this over, so we get kilogram second squared over meters cubed. And 10 times something, or times 10 to some other power, where we've got grams second squared over centimeters cubed. Okay. What are the powers of 10 here?
It's 10 to the 10th.
10 to the 10th here?
Yep.
And 10 to the 7th down here, is that correct? Or is it 8?
For the,
It's got to be 7.
Yep, 10 to the 7.
All right.
7, yep.
All right. I'm pretty sure it's 10 to the 7.
Yep.
Now, what I'm doing here is I'm erasing this centimeter cubed. I erased the thing over here, so the I don't know what you call it, that line in the middle, so that I could look at the units as kilograms per cubic meter or grams per cubic centimeter. What do we know about those units? What do we call units that are like this?
Density.
What's it?
Density.
Density. Okay. So what I'd like to do, I tried to find a natural set of units for this number to kind of integrate them. And what I found was these are off by 3 orders of magnitude, but then the density is a little weird because there's 1,000 kilograms per cubic meter of water and 1 gram of water per cubic centimeter. So I could unify these two things by saying it's times 10 to the 7th times the density of water, or 10 to the 7th times the density of water. Because the density of water over here is 10 to the 3rd power and 10 to the 1st power here. Okay? So I could say that that implies that G inverse is 1.49828 uncertainty 4 times 10 to the 7th power times rho 1 times second squared. I'll just put dots here instead of x's. Rho 1, right here, that's the density of water, which in this unit system works out, and this unit system works out. So I have a longer constant times the density of water times second squared. Because after all, the metric system was originally based on the density of water. Well, okay, that's pretty straightforward math, right? So the density of water is a factor in the universal gravitational constant. Why is water in the universal gravitational constant? The physical properties of water range over a wide variety of densities, except that at the bottom of a lake at 39 degrees, here on Earth, water keeps coming into this to be this reference density. There's the whole steam tables. Water exists as steam, water exists as ice. Water at different temperatures varies quite a bit. But the guys who made the metric system said, the density of water, it's a maximum density at 4 degrees Celsius. It's really, really stable, and water is incompressible. So it's actually the same, even if the atmospheric pressure grows a lot, water doesn't compress very much. It stays that same density. It's a wonderful reference because water's everywhere. So if you had an alien race and you wanted to describe density to them, you could by having a reference of the density of water. Okay? So I think that's extremely profound in just like almost no steps at all. There's like no thinking involved. It's like, I just wrote it down in terms of density of water. But there it is.
Wolfram Alpha confirms 4 degrees Celsius.
Okay. Mm-hmm. So it certainly is inside this range. Well, sorry, the the density of water just worked out the order of magnitude thing. The thing that got me out of bed, running down the hallway, almost doing a full Monty Archimedes to my computer, was this other number. And that number I recognized because I just had personal experience with this number. So I played the piano, I've tuned the piano by hand, I wrote software where I was picking out frequencies of the different notes by coming up with their Hertz number. And there's this one number that's at the heart of music. Music kind of has two sides. It's got the Pythagorean side, which is where physicists like to hang out. It's the part where if you divide a string in half, you get the octave. If you divide it different ways, you get whole number ratio multipliers to get from one frequency interval to another. So 3 halves, for example, a frequency ratio of two different frequencies, two different notes, one of them singing 3 times the frequency and the other one singing 2 times the frequency, well, whatever. If their frequency ratio is a half, it's called a perfect.
1/2 or 3/2?
It's 3 halves, a perfect fifth. So what you do with this number is you might take like 440 hertz, which is the concert pitch of A440, and then you would take that, multiply by 3 halves to get some number. I don't know the number. You would multiply by 3 halves to get the fifth above it. On a piano, you would go up 7 semitones. But on a piano, you don't get out the perfect fifth. This is a deep, deep mystery. The heart of music theory is that there's another side of how you can put notes together. You could also say 440 hertz, and then you multiply by a power of 2, a rational power of 2. In this case, it's 2 to the 7/12. That 12 right there is arbitrary. We could have 11 notes per octave, 12 notes per octave, 13 notes per octave. 19 is really interesting. When I did my senior project in math, it was Geometry for Teachers was the name of the class I was taking. In order to get my degree in mathematics, my bachelor's, I took this class and I studied this, and these are called temperaments. They're equal temperaments. They're equal divisions of the octave. Here we have 12 divisions of the octave. That's a standard ordinary piano. I also looked at 19 divisions of the octave. 23 is also interesting. 53 is interesting. But the reason why we do 2 to the 7/12 is that 2 to the 7/12 is almost equal to 3 halves. 3 halves is 1.5. 2 to the 7/12 is 1.498199270.8, and it keeps going because it's an irrational number.
That looks familiar.
That number is in that range. 20. 1.49820. Wait a second. Did I leave a number out? So I've looked at this way too many times. And I think I'm misremembering my number.
It's 1.49830.
It's this is, oh, I'm sorry. I'm remembering it's inverse. This is why I have to ask the audience to run the calculator for me. Please run the calculator. Please calculate 2 to the 7.
1.4983070, and it is right in that range.
Okay. Now we're in this range.
Yep.
Okay. that was like, okay, at this point, I'm getting out of bed, I'm running down the hallway, let me check this more carefully. Now I want to take 2 to the negative 7/12, which is the inverse of this. So now, because this number was G inverse, now I want to get back up to G. So what's 2 to the minus 7/12?
0.667419.
Not that I have that memorized.
No,
I just misquoted it a little bit ago. That number, that is inside this range.
Except for the digits off the beginning.
Yeah, except for the power of 10. But you'll notice this is a, let's see.
That's very.
Okay. See, as you flip it, it turns into the minus 8, and it ends up working out. So
that's what the classical folks were saying literally yesterday. It's like things are very interesting when you invert them.
Yeah. And so I almost want to call it Newton's blunder, but it was an arbitrary choice to put G in the numerator rather than the denominator. But really, G inverse is the one that holds all the magic. This number, I want to satisfy you with regard to how this is put together. So what I'm going to do is I'm going to write down the formula, and we'll check the formula, and I'll say what I think it is, and we'll verify it. Oh. So what I propose is to say that G is by definition, so I use 3 lines. The exact definition of it is 2 to the 7/12 times 10 to the 7th power times density of water times second squared, because we have units in here. So that's the 1.498, and then I take all of this and I invert it. So the reference density is 1, and this is 1 second squared, so both of these fall out. So I get 2 to the 7/12 times 10 to the 7th power quantity inverted. Can we calculate that number? I think it's already on the board, probably.
6.67419927, and wow, that's
times by 10 to the...
times 10 to the negative 8.
Well, it's going to be times 10 to the... Okay, times 10 to the negative 8, yes. Which is the correct number if you're working in a unit system where the density of water is 1. If you were working in the unit system where the density of water is 1,000, then this 10 to the minus 8 becomes 10 to the minus 11. Okay? So the density of water works in either one of these unit systems, or any arbitrary system that uses any arbitrary length or any arbitrary mass or any arbitrary time unit. So
I was wondering why you were expressing in the... Okay, continue, sir, sorry.
Okay, so this is more precise conjecture for an exact value of the universal gravitation constant. That is based on the physical properties of water at the surface of Earth. This is how water naturally forms on our planet, and it doesn't form exactly that density unless the planet is just this big. If the planet is smaller, it won't have the right pressure in the gravity situation. If it's much larger, it won't have the right pressure and gravity situation. It might be a little bit larger than Earth and have a little extra gravity because water is incompressible in the liquid state. So when it's 4 degrees Celsius on planets that are Earth or maybe a super Earth, you get the gravitational constant. Now here's the thing, is that some people think that maybe the way that the universe was put together is that there were a tremendously large number of trial multiverses that were all tried out. Like, let's try this universe. Oh, it didn't work. Poof. Let's try this universe. Oh, that didn't work either. Poof. Eliminate them. And so they continuously eliminate all these different possible universes, except ours just magically fell into place just so. But the thing is that there's no evolutionary pressure. There's nothing about the physical properties of water that would influence that equation. This is just any old mass. It's not just water doing this. This is all masses obey this kind of gravitational relationship. So this is my strongest evidence that some entity, I think, designed what our universe was going to be before the universe came to be. This is this very, very short chain of tight logic says Earth is a silicon-based life form. And so Earth is not the center of the universe. However, the main point, the whole idea, the reason for being, the raison d'etre, the central point of the universe is to make silicon-based life forms such as Gaia, Earth, the living planet. We're here as what the universe was intended to be. Because life. Okay, now that's not Archimedes' Law of Gravity. That's the universal gravitational constant. It absolutely is amazing to me. So now that I have this exact form of the universal gravitational constant, I can use that in places where we already are using the gravitational constant. There's something called Gauss's Law for Gravity. And Gauss's Law for Gravity can be written in many different ways. I don't have them all perfectly memorized. So the ones that I'm going to use are just, well, just the one I can remember here at the board. So Gauss's Law for Gravity treats the gravity as if it was a fluid. So it says that the flux, so given some volume, V, with boundary partial V, that contains some mass in this volume. And the shape of the volume does not matter because of the way it's proved. So the flux of the gravitational field through the boundary of the volume equals the divergence of the gravitational field inside the volume that's contained equals negative 4 pi times the triple integral of that volume. So the entire ball we're integrating over, not just the spherical shell, of G times the density of the medium, dV, equals negative 4 pi G M. This is what I call the third form, or C. The first one's flux, the next one's divergence, this one is density. This is Gauss's law for gravity. So to get to Archimedes' law of gravity, I'm going to substitute for G this thing. So now doing Archimedes Law of Gravity, I do the substitution, minus 4 pi triple integral of g, right here I'm substituting, which is 2 to the 7/12. Okay, 2 to the 7/12 times 10 to the 7th times rho 1 times second squared, and all of that to the minus 1 power. And then I've got rho, the density of the medium, I've got the differential of the volume, and that it ends up being minus 4 pi gm from here. Okay? That's the substitution. Now we do math. These go in the denominator, and the constants can come out. So I get minus 4 pi over this thing, 2 to the 7/12 times 10 to the 7th. Rho 1, I'm going to leave rho 1 inside the integral, but it's minus 1 power, so I have rho over rho 1 differential. And then I have the second squared to the minus 1 power, so it's second to the minus 2 power, which is kind of like the units. All right, that's Archimedes' law of gravity. What's so big? What's the big deal? Rho over rho 1. Rho 1 is the density of water. So this is the triple integral inside whatever volume of whatever shape of the density of the medium wherever you're looking at inside the volume. So if you had a volume encompassing this entire house, some places of the house are very dense, like the people, and some places not so dense, like the air, for example. But this integral combines all that together, does the whole thing, and this whole thing is one way to say here's the mass of the object. Okay, but it isn't really, because this is the density divided by the reference density, or the density of an object relative to water. So if you had a bottle of water in the house, the integral, if that was 4 degrees Celsius, the same pressure as like right here, that water would it'd be very, very close to the reference density. Reference density is 4 degrees Celsius and 1 bar of pressure. But this thing here, this rho over rho 1, has a name. And it's used in making beer and making wine. Engineers love to use it because it's a dimensionless number. Density has dimension, but then if you divide by another density, you get a dimensionless number. That's called the specific gravity.
Oh, okay.
Which is what Archimedes figured out about the crown. He measured the specific gravity of the crown relative to the density of the water.
Because if we use water as our reference frame, what happens to water at 4 degrees Celsius? Basically, as we looked, it was basically, it equaled out to like 1,000 liters for a cubic cubic meter of water, and then 1 gram was basically 1 cubic centimeter.
All of that.
Okay.
All of that. So what this is doing is it's taking, it's telling you how many more times massive the mass is relative to the same volume of stuff if that at the reference of water at 4 degrees Celsius and 1 bar of pressure. So you could have something twice as dense as of water, and this would end up being just a 2. Integral of 2 over the volume is just like, it's just plain old 2, right? So the mass and the volume, mass and length units have canceled. And the only unit system that we're left with is time. To the minus 2. That's also the unit hertz squared, if you're using seconds.
Oh.
But it turns out that there's something really amazing about gravity. It stays the same over time. So it's kind of like you're this is time independent. You're getting out some number of hertz here, but the gravitational constant is not contributing time to this. It's not part of this because this is time independent. It has second squared in there. But here we have an exact, closed form constant. So there's no arguing at all about what this number is out in the front. This is a dimensionless number that gets integrated over a volume. So you're going to end up with, it's going to have units. Is it going to have units of volume? It isn't really, because all that gets integrated away. You get this number.
Yeah, because if they cancel out and everything.
So volumes all cancel out. So this is dimensionless.
Well, that's fascinating because gravity is basically it's basically a form of acceleration and stuff, because basically you normally have your length term up in the top, and then we usually put mass in the bottom. You looked at it from going the other way, and then normally you have time squared in the bottom, and then when you have a length and a time squared term, basically that basically intuits acceleration.
Right.
But you managed to cancel out and come it down to a frequency.
Yeah.
That's cool.
So the force of gravity is in terms of a square frequency. There's no mass and there's no gravitational constant in this expression. I claim, based on this, that time is a fundamental entity. Time comes first before length and before mass. And gravity comes first before all these other things. Somehow gravity is here. You have to have a thing. It has to have some density. But in terms of this, the density just canceled out and we just have specific gravity, which is a dimensionless number, and the only dimension left is inverse time squared, which is inverse frequency. The way frequency works is you could take a short interval of time or a long interval of time, and you might get different numbers out, but they're still talking about the same physical vibrational frequency going on. So if you measured this by minute, instead of seconds you did minutes, or instead of minutes you did hours, it wouldn't really matter, because we have one of these frequencies here. So you can now scale the time all you want, and you'll change the name of your frequency unit. But
the
underlying thing is just this. So what I showed here is that there's a creator, maybe. This is suggesting that the universe, because the gravity doesn't just do water, it does everything. The universe was somehow thought up and designed first before it was made. It could have been a lab accident. You don't have to have an omniscient, omnipotent deity that continues. That could be, might not be. But this is really talking about the creation part. I'm Lutheran, so Father, Son, and Holy Spirit. This would be the Father Creator part of that Trinity. had thought up this first. And time is fundamental. So if you go to a physicist and you say, what, and you ask them, what's time? And they say, well, let me tell you about entropy. They're lying to you. They don't know that they're lying to you, but they're wrong. If entropy is where time came from, if I put a clock in a freezer and another one in an oven, they would somehow time travel because the entropy is different in those two different. It's wrong. So entropy emerges from time, but time is fundamental. Mass emerges from time. Gravity emerges from time. All these things emerge from time, but they start from gravity, and there's nothing about this that's quantum mechanical. I mean, there's waves. But that's a constant, that's dimensionless, and that's arbitrary. So there's Archimedes' Law of Gravity. There we are. Any questions?
The 12 was arbitrary, so what do you think about that now?
It's still true that that's arbitrary. You can make an instrument that has 19 notes per octave.
Yeah, but if I change that to 19, I get a whole different number here.
Yes, that's true. But if you change it to 19, what you're asking goes into music theory. And that's another lecture, but it's extremely well supported.
So let me, sorry, finish it.
So when you set, let's take your 2 to the number of half steps over 19, h over 19. You get 19 notes per octave. Great. You can play music on those 19 notes per octave. It's just fine. And what you get out of having this constant down here is you get music that is scale independent. If you make a lyre out of strings, you can't get scale independent music. You have to keep all of your music in the scale of the lyre. But if you make an electronic thing and you simulate these frequencies by a computer, you can get a list of 19 frequencies per octave. What's weird is that those are not very close to 3 halves, but there are a few notes in here that are close to 4/3, which is the major third. I think it's major third. No, it's the minor third, I think. So this is the perfect fifth, and this is an exact minor third in the Pythagorean world. But we're creating a new instrument that's equally tempered with a fixed number of notes per octave. And there are some notes in here that are very close to this. So a 19 note, you could make notes out of the minor thirds, but you would not be able to use the perfect fifths because none of these notes are really very close to that. But just by coincidence, 2 to the 7/12 is extremely close to 3 halves. We could do some math to show you how close. It's off by a little less than 2 cents. Yeah. So we did the math for G, but that math would be measuring how good this is in terms of music. The 3 halves would be out of tune by, I think it's 1.995 cents off from the 2 to the 7/12. But the measured value of the universal gravitational constant was down in the millicents area, like closer than 64 millicents. And the nominal value, I think it was off by 26 so 0.026 cents is 26 millicents. So the numbers are If you took those numbers to a musician and you ask them, is this in tune? They say, yeah, it's really, really precisely in tune. So very careful measurements of the universal gravitational constant are extremely close to 2 to the 7/12. So this is how close they end up being. So where people use 6.67430 uncertainty 1.5, in this realm we get G is 6.67420 with a 1. I'm ignoring orders of magnitude. But this is what people use today. This is what people ought to be using. In fact, they get another, it's even better. You get another 0 out here, and then you get the 1. Because it was 199, rounds to 200. So here we've gone up better than an order of magnitude in precision using this theory.
So now we have testable predictions.
Now we have, yeah, absolutely. Go rule that out. Experimental people, go rule that out. But I tell you, even ruling this in was a lot of work.
Mm-hmm.
That came from a group at the University of Washington.
That was about, what, like a year or so ago? It wasn't that long ago.
Yeah, it was several years ago. They earned, the 3 researchers that did it earned $1 million each in prize money for that number.
It's a lot of work.
Yeah.
How many hundreds of years?
Yeah. But also, I have the 2 to the 7/12 times 10 to the 7th, which is a whole nother story. So this here is about the geometry of the way the universe is put together. And it ends up being put together, pardon me as I whip this out.
Anybody that carries a dice bag is good in my book.
Decicus dodecahedron is a 120-sided fair die. It was built off of a dodecahedron, 2 to the 7/12. The minus 4 pi, there's minus 4 pi steradians of solid angle in a sphere. It's not just the surface area of the sphere.
What was the connection between the dodecahedron and the 7/12?
So if you had a dodecahedron that has 12 sides, 7 of those sides could be doing one thing, and the other 5 sides could be doing something else. I don't know what those are, what it does, but you could take 2 to the 7/12 of them doing one thing, and each of these points here is surrounded by 10 triangles. So those same 7 dodecahedron sides that makes the 7 and the 7/12 could also be doing the 7 into the 10 to the 7th, because there's 10 triangles here, and then 7 of those, I call these spinnerets, these points. So 7 spinnerets may be doing something, base 10 to the 7th, and then the basic dodecahedron divides it up by 12 so that 7 of those sides could do something. So this is telling a story about a Decicus dodecahedron that's surmounted by a spherical exponential casing in such a way that the 3 strong force color bearings are in a direct line with a panmetric fan. The latter consists of 6 score signature M ental vanes, so fitted to the ambifacient lunar wax and wane shafts that side fumbling of winding numbers is effectively eliminated whenever Alice and Bob Dozon tied their hyperbolic figure 8 wedding knot, complementary wedding knot, every time they kissed during parallel transport.
That may have been the most confusing sentence I've ever heard, but and somehow I think I'm like this. It seems that based upon the other things
But maybe there might be other things I am not telling you yet.
Well, no, I've connected it with
we've chatted before, so it's continue.
Yeah, so I'm pretty much done. I let's see, I proved the creator that Earth is a life form, silicon-based life form. Well, not proved.
It's infers. I mean,
Yeah,
maybe we have that
right.
1 in 10 to the 500.
Right. So I conjectured behind.
Cool.
And wrote down a law of gravity that didn't use the gravitational constant or mass in its expression, and showed instead that time is fundamental, or suggested at least, and suggested that there may be a place to be tying the complementary wedding knot out of a figure eight knot, hyperbolic figure eight knot, and its complement. When two of these things kiss, when they touch, there's a thing that happens, maybe. And during that touch, there's an opportunity to tie a hyperbolic figure eight knot. And then inside that whole arrangement, we get out the constants of nature.
I just literally typed into discus tricontohedron count 2.
Oh, they're kissing.
Yes, they are. Well, we can put it in the video, but right there.
Amazing. Okay, so I think that's enough. You know.
Yeah.
So there you go. Thank you.
That was awesome.